Oh, you have to do it with the Skype call.
Yeah. Hallo, guten Tag. Willkommen zu der Vorlesung Rechnerstrukturen. Wir waren ein bisschen zu spät. Es gab immer Überraschungen, wenn man etwas vor Online-Meeting planen. Okay, so Christian hat am letzten Mittwoch schon versprochen, dass wir screen isn't shared. Sorry, forgot it. Completely forgotten. Okay, Christian hat schon versprochen, dass wir heute ein Spiel hier machen. Okay. So, Rechnerstrukturen's algorithm. The first time I heard about it, I did not understand that. The second time I heard about it, I did not understand that. The third time, when I had to attend an exam, I understood that. After that, I forgot that again. So when did I actually remember that? When I play a game. Okay, so I think it's also natural that let's do a game here. So how many interns do we have here? Let's count. So das ist 1, 2, 3, 4, 5, 6, 7, 8. So, I need 8 volunteers. The minimum will be 7. I can play one of the 8. But it would be the best to have 8 students who will be interested to be here. And our problem now is that we have a wrong cable. So if you agree to be here, it will be broadcast to YouTube. You would agree on that if you volunteer to join us at the stage. And I'm setting up the stage now. Okay, do we have students who are interested to join us to play the game? Otherwise, I'm not able to do that. You should not point the others. You have to volunteer by yourself. Okay, so who wants to join this? Please raise your hand. Or please join the stage directly. Without students, we are not able to play this at all. Yeah, please. Please. Yes, please. 3. So, please. So we need still some more. We have now 4. No. No. You don't have? You don't have? It will be my puppet. Join us game, please. Just join. No. The question is whether winner wins anything. No, sorry. What I can say is that for those who are here today, I think you would remember Rechnerstrukturen's algorithm, okay? For those who are watching, I'm not sure. Okay. So We need two more, yes, please. Yes, please. Okay, yeah, you too, please. You as well. Okay, so let's start. So you get x1, not x2. Don't look the other side. I could not find the correct assignment. So use the written one, okay? So.
Thank you very much.
The written ones, not the. Okay, so not the other side with the written ones. Okay, so first thing first, we have 4 literals, right? So x1, we have 4 variables: x1, x2, x3, and x4. We have also 8 literals: x1, not x1, x2, not x2, x3, not x3, x4, not x4. First thing first, please group yourself. Okay. If you have no negation, you are group 0 here. No, if you have 1 negation, you are in group 1 here. Okay. If you have 2 negations, you are group 2 here. If you have 3 negations, you are group 3 here. Okay, please put yourself into group. You have no negation, so you are group 0.
But here I am.
You have no. This side, please. Okay, and you have 1 negation, 1 negation, 1 negation. Have 2 negations. Sorry. You have 3. Okay, so let's keep some distance between groups. Okay, so we have in total group 0, no negation. Group 1, 1 negation. Group 2, 2 negations. And group 3, 3 negations. Yeah, these 2 are 2 groups, right? Remember that. So the first thing is that we are going to use the resolutions rule. The resolutions rule says that if you want to shorten 2 terms, they are almost the same. They are basically the same in all places except 1. So that means that if you have 0 negation, you will not be able to have any chance to apply the rule with this group and this group. Okay, so group 0 can only match group 1. Group 1 can only match group 0 and group 2. Group 2 can only match group 1 and group 3. You cannot do any further. Look at your next group. Up to here, clear? So let's start with this. So let's put one of each other to see. So these 2 together. Can they become a couple? Oh, sorry. Can they use the resolution sets to reduce 1 variable? So that means that x1, x2, and x3 would be the correct answer, right? So we get for these 2 an x1, x2, and x3. And where is that? Where is 1, 2, 3? 1, 2, 3, 2, 2, 4. Okay, here. So you get x1, 2, 3 because of this. Okay, now let's step back. And now the second one.
All right.
So, not yet. Okay, so now let's keep this aside for a while. Yeah. Fairer. Okay. I have a fast linker gamma. Okay. Ik zoek hier. Okay. So, x1, x2, x3 muss finden. Es gibt keine. I don't see any. Can you find out x1, x2, and x3?
X1 is.
We find it somewhere. Okay, these 2. They are the same except x2 and not x2. So they 2 can also be reduced by this one. Yeah. Okay, so now let's take this one. Now you're back again. So it's also not correct. I will find out the correct one at some point. So now these two, again, almost the same, but with one difference. So this would result in x2, x3, x4, right? So now for you, we get x1, x2, x3, x2, x3, x4. This is correct. And I don't have others. Okay, Daniel is writing that we will get them soon.
Which one are you?
We are lacking x1, x2, x3, and x1, x3, x4.
X2, X3.
Okay. Okay, so now you can go back. Okay. So from his perspective, he can merge with all the three midterms and then get the three simplifications. Let's look at these two groups. Okay, so now let's start from you. And let's start with you two.
Okay.
They are almost the same but different. Can we put them together? No, because they are so different, right? So now you can go back. Let's take the next one.
Me?
Yes. So you get these two. Yes, Varun?
Because x1 and x3 are totally different from both sides, and x4 and both x4 and right?
You have to be almost the same except one position. Okay, good. So not. So set, yes. Okay, so yeah, sorry, you cannot match with any of them. So now let's don't go back. Let's try the second one.
Yeah,
So what do you get?
it's working.
It's working.
Yeah.
That's a good. Which one should go?
X2, X3, and X4.
Not x2, x3, x4. X1 is gone. Okay, so we get this one. So I keep it on your side. Let's take the next one. So now you're back. Let's take the next one. So again,
Ja, okay, X3 ist weg. Ja,
so extra is back.
ja, okay.
So what is that? X1, not x2, x4. X1, not x2.
x2, x4.
Okay. Yeah, here. All right.
Müssen die beide jetzt halten, oder?
Okay, nice. Okay, and the next one. So weg. Okay, good. So, kann das zusammen? Ja oder nicht? Nein. Huh? So, dann, du hast die zwei richtig geschafft.
Ja.
So, komm draußen. Ja.
Oh, du schon.
So, das ist, kann man zusammen machen. Na x1, x2, x4. Na x1, x2, x4. So, yours. Let's take the next one to the stage. No, let's just take this out. Okay, continue. So, die zwei zusammen kann man machen. So, das ist na x1, x3, x4. It's working, yes, good, very good. Let's take the next one. So, who is missing? You?
No.
No, not yet.
No.
You three? No, I think one of them has not matched with him. Yeah.
Don't work.
No. See you. Okay, now it's turn. Okay, now we try the last one as well. So you match with him. So. No. No. Yeah. Up nine. Okay. Yes.
Yes.
Can I have a look? What's that? This one. Not x1, not x2, and x3.
Yes.
Okay, let's keep here. Now I need to get all the right signs back. So can I take all the right with me? No, not yet. Let's count. Okay, so what we need to do is to check whether each of them is already a prime implicant. Right? How do we check that? So that means that we have to check whether any of the red terms has an exact short term of this. Right? So let's take off this one. So let's distribute the white papers a bit so everyone can play a while. Okay. So, we only have 7 left. Maybe you give me a hand. Don't run away, okay? So, I'm naming the mean term. And if you are a short term of the mean term, raise your hand. Okay? So I'm reading the mean term here. And if you are a short term of the mean term I'm naming, please raise your hand. Okay, so x1, sorry, wrong side. x1, x2, x3, not x4. Good. A short term of x1, x2, x3, not x4. Yeah, so you are, right? So x1, x2, x3, x4. Okay, good. x1, not x2, x3, x4. x1, not x2, x3, x4. No. Let me do it again. x1, not x2, x3, x4. Yeah. You are a short term of this, right? You don't have x3.
Oh, yeah, I do.
Okay, raise your hand, please. Okay, good. So far, what can we say? The 3 mean terms I just spoke have the real short terms. So those 3 are not the prime implicants. So we just go ahead. The next one, not x1, x2, x3, x4. Not x1, x2, x3, x4. So, okay, good. Yeah, x1, not x2, not x3, x4. x1, not x2, not x3, x4. x1, not x2, not x3, x4.
Not x1, x2, no.
X1,
Don't work.
not x2, x3, and x4.
It should be not x3 there.
It doesn't match.
x1, not x2, not x3.
x1, not x2, not x3, x4. x1, not x2, not x3, x4. Okay? You cannot say that it's not the same. Of course, it's not the same because you are a short term of that term. Okay, the next one, not x1, x2, not x3, x4. Not x1, x2, not x3, x4. So you are the actual shorten. So not x1, not x2, x3, x4. Okay, good. Not x1, not x2, x3, not x4. Okay. So what have we learned up to now? What we have done so far is that we basically try all combinations of the pairs, and then we basically generate their real short terms. And after generating their real short terms, we check whether any of them over here can be somehow shortened by one of them. If we find one of them that is not possible to be shortened, that is a prime implicant. So far, what we conclude is that none of them is a prime implicant in this round. Okay? So let's move on. The next round. Again, group 0, group 1, and group 2. Sorry, you are wrong. Okay, again, the same policy. Group 0 matches group 1. Group 1 matches group 0, but it's already done, and matches group 2. So let's start from the first one. So these two. So are they close enough? No, yeah, to look. Let's take the second one. You stay. No. So if they have different variables, they have no chance. Yeah, they must have the same variables. Okay, next one. Okay, good. Okay, good. So what have we learned so far? He will stay alone for a while, and they will become a prime implicant later on. Yeah. Okay. Good. The next one. So 2, 3, 4. 1, 2, 4. No. Okay. Good. Next one. 1, 2, 4. 2, 3, 4 doesn't work. 1, 3, 4. 2, 3, 4. Then okay. So you will stay back. Oh, no, it's one more. Sorry, I remember there's one reduction here. So we get one shorten. So let's generate this shorten, right? X3, X4. Okay, so then let's keep that in mind. So then you start from here with her. No chance. Go back. Let's go to the next one. Also no chance. It's a different index, okay? So yeah, the next one, no chance, different index. Go back, no chance. So sorry, this matching doesn't work, so please. Okay. So now, again, I'm going to take this one out, but you can keep this one, right? So now we go through all the terms we have, all the white papers. So we have generated X3, X4, and X3, X4. Let's ask each of them. So X1, X2, X3 is not shortened by X3, X4. So this is a prime implicant. X1, X2, X4 is not shortened by that, so that is a prime implicant. Now X1, X2, X4 is not shortened by that, it's a prime implicant. Now X1, X3, X4 is shortened by X3, X4, so I take it. Now X2, X3, X4 is shortened by X3, X4. Yeah. So this is also nothing. Okay, so then now X1, now X2, X3 is not shortened by X3, X4. So in this round, we find 4 prime implicants. All of them are the prime implicants. So after this round, we have only one left. That is X3, X4. And then, of course, in the next iteration, this is a prime implicant as well. Okay, thanks a lot for help. So this explains the process of Quinn-Markowski's algorithm of finding the prime implicants. So what have we done? First step, we group the terms. So basically, we group the monons. At beginning, we have a group of no negation, one negation, two negations, and so on and so forth. Because of the rule we want to use, you would not be able to cancel two monons, or you would not be able to merge two monons into one monon if they have more than one different positions in the negations. So group 0 would then match with group 1. Group 1 would then match with group 2. Group 2 would then match with group 3, like what we have done over here, one by one. And if two monons can somehow be really shortened, then they would generate one new monon. And that new monon would be the real shorten of the two monons that we use for generating that shorten. Okay? So after this process is done, at the end of this one, we have generated the monons that have one less literal. And then we check whether some monons are already prime implicants already. And for those prime implicants, we can already put them into the list of prime implicants. And at the end, we go through the list until we don't have any monons left. Then we have found all the prime implicants in this, for this input. This is the most general solution that you can use to find the monons, the prime implicants. And yeah, this is a general solution. It's not limited to the number of variables. Okay. Any question about Quinn-Markowski's algorithm of finding the prime implicants over here? So this is actually the process we have just been doing. So it means that we are looking at, in each iteration, the number of minterms we have. Okay? So according to what we have done, we got four prime implicants with length 3, and we got one prime implicant whose length is 2. Okay. Any question for Quinn-Markowski's algorithm and K-file diagram? If not, then I suppose we go ahead to talk about the hazards. Hazards. Was bedeutet Hazards? Bisher haben wir nicht über Realität geguckt. Ich habe schon gesagt, diese Vorlesung ist über die Hardware von Rechnern, aber wir bisher sprechen nur über Mathematik. Ja, es gibt nur zwei Varianten, nur und eins. Und wir haben bisher nur und eins bearbeitet. Aber es gibt natürlich ein bisschen Unterschied zwischen solchen Mathematikmodellen und die Realität. Solche Abweichungen zwischen Modell und Realität ist mit Hazards genannt. Und Hazards sind ärgerlich, aber normalerweise unvermeidlich. So, es geht auch für technisch realisierte Schattennetze. Und wir müssen immer am Ende gucken, ob unser Mathematikmodell implementierbar sind. So die zentrale Frage für unser Schattennetze ist, was passiert, wenn die Eingaben wechseln. So, natürlich, die Ausgabe kann wechseln, aber die Frage ist, ob solche Ausgabe wechselt nur einmal oder wenn diese Ausgabe nicht wechselt, wechselt das Schattennetz seine Ausgabe auch nicht. So, aber die Realität ist, dass wenn wir von f von x, so von f of x ist nur, dann nehmen wir von x bis y, so dass die 2 hat nur ein Bit Unterschied. Diese f von y ist 1. Unser Wunsch ist, dass das Schadnetzwechsel nur einmal von 0 zum 1. Und wenn f von y nur ist, dann wünschen wir, dass dieser Schadnetz nicht sich wechselt, aber in Realität das Schadnetz kann Ausgabe zwischendurch wechseln. Das ist mit Hazards genannt. So it looks a bit complicated at the beginning. And you can say that, is this really possible? So I have a function f implemented with a circuit. And I change the input from x to y. If I only change one bit from 0 to 1, I change the input. If f of x is 0 and fy is 0, I would expect that there's no change, right? And if f of x is 0, f of y is 1, I would expect that this circuit changes only once, from 0 to 1. If you do not manage that well, or if you do not think about this carefully, it's possible that your circuit, you think that it changes only from 0 to 1 once, but it changes multiple times. Or if you think that the circuit doesn't change, yes, it's correct. It doesn't change at the beginning and at the end, but whether it changes the value in between. The question is not only the final product, but the intermediate steps. We have up to now never checked this case. Okay? So, das machen wir weiter. So, es gibt verschiedene Hazards. Hazards sind statisch, dynamisch, es gibt Funktionshazards und Schattungshazards. So, statisch Hazards ist für dieses Beispiel, wenn f von x und f von y beide gleich sind, der Ausgabewert soll gleich bleiben, aber das Schadnetz ändert sich. Für dynamisch Hazards, also ist von dem Fall, dass f von x ist 0, aber f von y ist 1, oder f von x ist 1, f von y ist 0. Der Ausgabewert soll sich ändern, aber ändert sich mehrfach. Nicht nur einmal, aber mehrfach. Okay? Dann solche Hazards kann schon in Funktionsdefinition enthalten. Oder solche Hazards ist nicht bei Funktionsdefinition enthalten, aber durch die Art der Schattung entsteht. Wenn die Funktion hat schon Funktionshazards, dann haben wir fast nichts zu tun. Wir brauchen etwas anderes, diese Dinge zu vermeiden. Das sprechen wir nächste Woche. Oder vielleicht schon nächste Woche. Ja. Mit Schattungshazard. Solche Hazard ist nicht gut. So, es bedeutet, die Funktion kann man richtig implementieren, aber weil wir nicht richtig Schattungs entwickeln, gibt es solche Hazards. So, man muss doch noch überlegen. Okay, so, dann gucken wir die zwei verschiedenen Hazards mehr genauer. So, Funktion f ist eine Funktion mit n Eingabe und die Ausgabe ist entweder 0 oder 1. So, solche Funktion hat statischen Funktionshazard, wenn diese passiert. So, es gab zwei Bitvektoren a und b. Die zwei Bitvektoren sind hatte gleiche f von a und f von b. Und wenn es gibt einen anderen Bitvektoren c, für diese Bitvektoren c, jedes Bit ist entweder von A oder von B. Okay? So, wir haben zusammen A und B. So, A ist ein Bitvektor, B ist auch ein Bitvektor. Dann für C, so dieser C ist für jedes Bit entweder von A oder von B. Okay? So, die statische Funktion Hazard passiert, wenn es solche C gibt und f von C ist nicht gleich von f von A. Das ist ein bisschen zu schwierig in dieser Logik zu verstehen, dann gucken wir mit einem Beispiel. So, wir haben eine Funktion mit 3 Variablen, x1, x2 und x2 und x3. Und dann gucken wir jetzt mit dieser, die 2. So, das ist A und das ist B. Okay? So, A und B sind 2 Bitvektoren und f von A ist gleich von f von B. Und dann es gibt C, und diese C, jedes Bit ist entweder von A oder von B. So, es kann sein, das ist unser C. So, dieser Bitvektor C, für die 2 ersten Bits sind von A und das letzte Bit ist von B. Okay. Es gibt auch diese Möglichkeit, dass wir diese C hier nennen. Ne? So, dieser C Bit gleich, die erste und letzte Bit sind gleich, die ersten 2 Bits sind gleich von B, das letzte Bit ist von A. Okay? So, und dann haben wir schon gesagt, so f von C ist nicht gleich von f von A. Ja? Was bedeutet jetzt hier ist das? So, wenn wir jetzt hier gucken, von die 2 Bitvektoren zwischen die 2 Bitvektoren nur und nur 1, 1. Es gibt 2 Bitvektoren, so nur 1, nur und nur 1. Dann dazwischen, wenn wir von A nach C wechseln, gibt es auch die Möglichkeit, unser Schachtelnetz auch dazwischen am anderen Funktionswert wechseln und dann zurückgehen. Okay? Is that understandable? So you have these 2 values, 2 bit vectors, 0, 0, 0, and 0, 1, 1. F of 0, 0, 0 is the same as f of 0, 1, 1, right? Now, we just change the input from 0, 0, 0 to 0, 1, 1. You expect that there is no change of your output. But somehow you change your input slowly, but not at the same time. Instead of doing 0, 0, 0 to 0, 1, 1, you first change from 0, 0, 0 to 0, 0, 1, and then to 0, 1, 1. Or from 0, 0, 0 to 0, 1, 0, and then to 0, 1, 1. If you don't change these 2 at the same time, and exactly at the same time, you have the possibility that your circuit jumps into the other region that you did not want. And if that happens to change to 0, your circuit changes the values over time. That's vision in the middle. So it changes from here to here, or from here to here. Okay? So, das soll alles hier sein. Okay? Gibt es Frage über statische Funktionshäuser? Any question? Okay, good. So the functions hazard is very simple. That you think that there's no change, but because you cannot change, you do not, if you have some possibility that you do not change your inputs at the same time, then between you change from A to B, you result in some status that is part of A and part of B. And if that happens and you actually have to change your value, then your function has an hazard. Okay. So that is statisch. Und was ist dynamisch? Dynamisch Hazard ist ähnlich, aber jetzt als anderes Thema. So, wir haben zwei Vektoren a und b. F von a ist nicht gleich wie f von b. Okay, das bedeutet, wenn wir die Eingaben gleichzeitig ändern, dann sollten wir die Schaltung von 0 zum 1 einmal beobachten oder von 0 zum 1 einmal beobachten. Aber natürlich, wenn es gibt auch mehrfach dazwischen, dann wechseln wir mehrfach. Okay? So, dann das ist auch ähnlich. Wir machen zum Beispiel von hier, so von 1 zum 0, ich bin unsicher, welche die Aufgaben wir haben. So, von 0 zum 1. Oh, ich glaube. So, was kann eventuell bei einem Wechsel zwischen den Eingaben 0 und 1 beobachten? So, von 0 zum 1. Ja? So, das ist von 0 zum 1. Also 1 zum 0. So, gucken wir machen noch einmal. So, hoffentlich. Let's hope this functions again. I think I'm using the wrong link. This is the public link, so it doesn't have the correct answer yet. So I'm not going to click a version that all answers are incorrect. But you will get a correct answer after today's lecture. So 0 zum 1. So das ist, hier ist 0, hier ist 0, hier ist 0, hier ist 0, hier ist 0. Von hier zum hier. Okay, so I think we can have a look. I forgot to start, sorry. Always forget that.
I think the counter is bugged. Last time we had like a negative number.
We got a negative number?
Last time.
Less time.
So I think the camera is just not reliable.
Okay, good. Okay, so the answer is that, of course, it changes from 1 to 0, but multiple times. Why does that have multiple times? Let's go back to the slides. So if you're not able to change the inputs always at the same time, then you will have the possibility that you somehow only change the inputs from 0, 0, 0 to 0, 1, 0. So then you are here. And then you change to 0, 1, 0. And then you can change to 0, 1, 1. And then it changes to 1, 1, 1. So it can be also opposite. You can change from 0, 0, 0 to 0, 0, 1. And then from 0, 0, 1, from 0, 0, 1 to 0, 1, 1, 0, 1, 1. And then from 0, 1, 1 to 1, 1, 1. Okay, you can also change from 0, 0, 0 to 1, 0, 0, and then to 1, 0, 1, and then to 1, 1, 1. Okay? You can also continue from here, and then move here, and then move down. So what happens is that if you are not able to change the inputs all at the same time, then you are risking your circuit to change the values multiple times. So with that, because you are changing from 0 to 1 or 1 to 0, you need two intermediate steps to achieve that. And this is called the dynamic hazards. Okay? Gut. So, Zusammenfassung. Es gibt zwei verschiedene Hazards, statisch und dynamisch Hazards. Wir haben richtig Schadnetze für diese Funktion Implement entwickelt. Aber das, wenn wir zwei Eingabenvektoren haben, A und B, und f von A gleich von f von B, am Ausgang von dieser Schadnetz liegt kurzzeitig ein anderes Wert an. Das ist statisch Hazard. Für Funktionswert ändert sich f von A nicht gleich wie f von B. Am Ausgang von S ändert sich der Wert mehrfach. Das ist dynamisch Hazard genannt.
So, if I understand it correctly, statischer hazard, it means like when we change only once, but dynamischer hazard, it's when it's like statischer hazard, but we use it like multiple times, so to say.
Not really like this. They imply the same thing. So the reason for the static hazard to have one value in between is because you have the same outputs, right? Mm-hmm. So f of A is the same as f of B. You need to change to something that is different from these two. And then you come to the f from A to B.
Nachbar.
So you only need once.
Mm-hmm.
Okay? But with dynamic hazard, you are changing from 0 to 1. And then it's to go back to 0 and then to 1 because you have different outputs. So if you originally only need to change once, now you need to change 3 times. Otherwise, it's not possible to reach that. So you need two additional steps in between. So you change from 0 to 1.
Yeah.
And then if you want to say you originally only need to change once, right? But now you change multiple times. If you change from 0 to 1 and it always stays as 1, then it's fine. It's not dynamic hazard, right? So if you change from 0 to 1, and then you also again change it from 1 to 0, and then change from 0 to 1, and you have multiple
Hazards.
changes and in between. That's called dynamic hazards.
Okay.
Okay? Okay, so so das haben wir schon gesprochen. Wir haben A und B, dazwischen bekommen wir anderes Dinge. So deswegen haben wir dieses Problem. So die Zentral von diesen Aufgaben ist dieses Dazwischenkonzept. So was bedeutet dazwischen? Das haben wir schon kurz schon gesprochen. In Bezug auf Eingabewechsel. Das bedeutet, wir haben etwas von Big Vector A und Big Vector B zu wechseln, aber diese sind nicht immer vorliegend gleichzeitig. Dann müssen wir diese aufpassen. Ja? So, wenn wir noch einmal über KV-Diagramm gucken, so dieses Konzept von dazwischen ist einfach kann man mit diesem kürzesten Weg im KV-Diagramm beobachten. So, wir haben 2 Big Vektoren A und B. So, A ist nur und B ist 1, 1, 1 nur. Dann die kürzeste Weg im KV-Diagramm von A zum B zwischen A und B ist einfach dieser Richtung oder diese Richtung oder diese Richtung und die alles Richtung dabei. So, es bedeutet, wenn wir wenn wir die drei verschiedene Bits beobachten möchten, so von nur zum 1, 1, 1 nur. Wir haben die 3 Möglichkeiten, Wir haben die Möglichkeiten, dass wir die Geschwindigkeit von Eingabenwechsel haben. Und da müssen wir die alles richtig machen. Okay? Gut. Funktionshazards sind in Realisierung von Schadnetz nicht zu vermeiden. Das können wir nicht machen. Leider. The only way to solve functions hazards is to avoid changing the inputs, not at the same time. You will need to change the inputs at the same time. Okay? So, why am I always back and forth in the slides? Aber es gibt auch Schattungshazards. Für diese Vorlesung für uns das Schattungshazard ist interessant. Es bedeutet, die Funktion hat kein Hazard, aber das Schadnetz hat Hazard. Das kann nicht sein. Das muss man vermeiden. Und das müssen wir gucken. So, wie kann das passieren? Und kann man das den Schattungshazard vermeiden? Okay, so was ist Schattungshazard? So statisch Schattungshazard, wenn es A und B gibt und diese Funktion bezüglich keine statische Funktionshazard, aber wenn wir von Eingabewechsel von A nach B, dann ist es nicht stabil. So, es bedeutet, wir bei Beobachten dazwischen etwas anderes. Okay? Für dynamische Häser, das ist auch ähnlich, aber wir können jetzt mehrfach von f von A nach f von B, aber es soll nur einmal wechseln, aber wir bekommen mehrfach solche Funktionswechsel. So, solche Auftreten ist nicht garantiert, aber kann passieren. Das ist immer ähnlich. So, vielleicht Sie haben die alles Dinge im Labor getestet, alles in Ordnung ist, aber auf Field es ist nicht richtig. Das ist schwierig zu sagen, ob es ist ein Bug oder ein Feature. So, gucken wir jetzt. Es gibt zwei. Diese Funktion f. Für diese Funktion gibt es kein statisch Funktionshäser. So, nehmen wir an die zwei Big-Vektoren a und b. So, f von a und f von b. Beide sind 1, aber es gibt kein Dazwischen. Es gibt kein Dazwischen. So, there's no C you can define because they only have one bit difference. So according to the definition we had earlier, we expect that there's no hazard, right? There's no function hazard, but let's have a look of what we get. So for diese Big-Vektoren haben wir schon früher geguckt, oder nicht? Egal. Wir machen jetzt sofort. So, wir machen jetzt mit 2 Minuten die 3. Oder, ja, das machen wir einfach. So machen wir jetzt mit Mintermen, okay? So, das ist hier ist die zusammen 4 Mintermen. So, das ist na x1, na x2, x3 out, x1, na x2, x3, and x1, x2, na x3, and x1, x2, and x3. Okay? So, dann können wir die zusammenbauen. So, das nennen wir jetzt mit die zwei. Die zwei aus einer Gruppe. So, die zwei aus einer Gruppe und die zwei aus einer Gruppe. So, das ist gleich wie x1, x2 oder x1, x3. x2, x3, sorry. Any question for this? Now you build a circuit over here. And let's have a look of what happens in this circuit. Okay, so now, if we do not change the input, there's no chance to change, there's no input between between 111 and 101. What could be the possible reason that we somehow have lead hazard? Let's look at the circuit. If some AND gates need longer time, then your signal could be delayed. So we need to create a difference. So nothing is perfect. Between the input and output, there is some delay. If one AND gate comes from an unknown company, that could be faster, then the company that has to guarantee some solar gate models, right? Or you take someone that says, I have a fastest AND gate. From one of them, another says, I have a very slow but very energy efficient AND gate. Then you could get different matches over there. So if they are different speed, then you may get a problem. Let's see what happens. over here. Okay, this is there. So global, das ist 1 von x1, x2 und x3. So 1. So das ist 1 und 1, so ist 1. Hier ist die Negation von 1, hier ist nur und 1 ist nur, so diese Ausgabe hier ist 1. Okay? Das ist richtig. F von 1. Jetzt wechseln wir x2 von 1 zum nur. Okay? Dann, diese Negationsrate ist normalerweise schneller. So, dann bekommen wir hier aus 1. Okay? Then the next question comes. If the upper gate, this AND gate, if this AND gate is faster and much faster, then it would change from 1 to 0. And then in this period of time, you get 2 zeros. 0 or 0, the output of this function will become 0. And then later on, the lower AND gate really reacts, outputs 1, and you get a 1 over here. So that means that it looks like this is a good design, but it's not a correct design. So let's do it again. So, mal noch einmal. So wir haben dieses Schatnetz. An diesem Schatnetz bauen wir x1, x2 und oder nicht x2, x3. Dann nenne ich an, dass das Schatnetz, das Endgatter von oben ist mehr schneller als das Ungatter unten. Okay? So, dann jetzt wechsle ich x2 von 1 nach 0, weil das Gatter hier schneller ist, bekommen wir dieses Signal früher als nur. Dann ist es nur. Dann in diesem Zeitpunkt, die beiden Signale, hier ist nur und hier ist auch nur. Dann das Konjunktionsgatter hier würde von 1 und nach nur wechseln, weil beide Eingaben nur sind. Okay? Natürlich danach, wenn diese Ungatter richtig berechnet, dann bekommen wir am Ende 1. Aber dazwischen beobachten wir vor ein paar Nanosekunden oder Mikrosekunden, natürlich Nanosekunden oder Pikosekunden, ein bisschen anderes. Das ist Einschätzungshazard.
So I have a question. So if I understand it correctly, so the one that was a little bit faster, so it already calculated that it's 0, but the one that is a bit slower, it didn't calculate yet. It hasn't calculated yet, but it had the value null because 0 because it didn't calculate.
So the signal is not just gone. It's always there.
Because
You cannot say what is 0 or 0. It's of course 0, but then the question is how long does this 0 last? It lasts until the signal changes.
It's because of transistors, because 0 means that there is no... Okay, I understand.
If it's 1, then it stays as 1. And then until you change the signal from 1 to 0, it will be 1, right?
So, and that process is called Schaltungshazard.
That is a Schaltungshazard, yes. Such a hazard is Schaltungshazard. I just realized that we are really too slow today, like usual. We have 5 minutes. Somehow we have to give up the room earlier today. So how do we avoid Schaltungshazard? Well, yes. This problem can be avoided. And this is the good news. It's not something you cannot solve, but it's not free. You have to pay some cost. Which cost do you have to pay? There's a law by Becher in 1965. He said that to avoid static Schaltungshazards, you just need to make sure that you use all the prime implicants. A very simple solution. There's a proof why this is the case. I'm not going into the proof. Let's assume that this is correct, because I think we never test students the proof. If you're interested, have a look at the proof. Do the proof on your own, or watch the YouTube channel from last years if you want to check the proof. But I think every time I said I don't do the proof. So maybe when you watch YouTube channel, you will not be able to find a proof anyway. But the proof is very self-understandable. It's also very simple. Basically just said that if it's a prime implicant, if it's a prime implicant, then the good thing is that if something is slow or fast, if you change the signal, you don't care. We just said earlier, right? It's not that you don't, when you simplify x1, x2, x3, x4, together with x1, x2, x3, not x4, you don't care what happens with not x4, with x4. You really don't care, and you also use that to somehow make sure that if a change of the signal is due to one of these midterms, you don't care, because there's another guy covering that. So that is the reason why you keep all the prime implicants. So now let's look at this case that we have the function we had earlier. We had those 4 midterms as we explained earlier. If now we do the K-file diagram, so now let me do the K-file diagram again. So we have x1, x2, and x3. So what we get is 0, 1, 0, 0, 0, 1, 1, 1. Right? If you don't know what I was doing, go back to check K-file diagram, and then make sure that you are able to do it just blindly. And then you get all the full marks for the exercise and the exam for those K-file diagram. So we look at the prime implicant. So we look at the size of A. There's no size of A. Size of 4. There's no size of 4. Size of 2. So we found some of the size of 2. So let's start with the first one over here, and the second one over here. And there's often missed the third one, but for this case, this is not forgettable. So there's a third one over here. Okay, so there are in total 3 prime implicants, not only 2, right? 3. When we talk about the coverage of prime implicants, we look at the minimum cost. If it's the minimum cost, we only use I should give them different colors, right? So let me give this one. I want to use the red one. So let's say this red one. We would use the red one and the cyan one, the blue one, because you only need 2 prime implicants to cover the 4 ones. But this results in a possibility that when we change the inputs, it's possible that the signal change in between would result in the change of the output. So if we use all the 3' implicants, that would be the 3. And let's have a look of the 3. So it's a x1, x2, not x2, x3, or the x1, x3. So this was somehow dropped out when we look at the K-Val diagram with the minima cost. So basically, we build this additional circuit, this additional AND gate, and then let's see what happens. Oops. So I don't have that anymore. So you can try this one. And because the good thing is that when you change this input over here from 1 to 0 or from 0 to 1, the good thing is that if the output is 1, this circuit will guard the correctness. Over here, this correctness of 1 is somehow guarded by this additional prime implicant we put back. And why is that guarded by this prime implicant can be checked with the proof that I skipped earlier over there. So now, as a hazard, so the key part of hazards is like the hazards are somehow not convenient for us to organize such stuff, but it appears. So the key part to understand the hazards is to understand that there are 2 types of hazards. The function hazards are somehow difficult to handle using any other means unless you clock the signal such that you change the inputs all at the same time and all circuits operate at the same time to make sure that you don't actually have arbitrary changes of your system. For functions that have no functions hazard, but somehow your design of circuits with the minima cost may result in such circuits hazards. You can avoid them by using all the prime implicants. This is a bit more costly, but it's implementable. Alternatively, you could look at this interesting solution that is shown over here. Does anyone know what this means? So there's an interesting circuit. There's a very strange way of looking at the number 4. If some gates are faster, let's make the signal delivery slower. How do you make the signal delivery slower? Let's make a longer path for the signal to deliver. So to handle the mismatch of the speeds of the gates or the other components, you somehow detour your circuit and to make them change almost at the same time. So if the hazards are only due to the latency difference of the gates, then you can somehow make the connection longer and then match the different speed such that all the speeds are almost the same and you don't have to suffer from the different speeds of the gates. But in general, the fundamental solution is not to do any of the stuff we discussed today. It's to have so-called clocks of the circuit. So you will need to define clocks. If you have the definition of clocks, then you don't have to worry about anything in between. Everything is triggered or handled at the clock, and there's nothing in between. And with that, you can avoid those hazards we discussed today. It's basically the fundamental solutions. And also because of this reason, the computer systems do not just work in a discrete value domain, because you have already known that we cannot operate the continuous values. It's just impossible to do that. We have to operate in a discrete value domain. And because of the stuff we discussed today, the computers are also not able to handle computing in a continuous time domain. It's impossible to design a sorry, I take my words back. It's extremely difficult to design a circuit that is correct without clocking. Without clocking, you would have to check all the hazards are avoided. You would have no chance that your circuit changes the value to arbitrary values in between. Otherwise, with that, you will need more efforts. With clock, it's easier in designing a system such that you have the precise timing. And with those precise timing, you are able to control your circuits better without hazards. So the last part of this part one of computer structures is to talk about the clocks. With that, since I'm overclocked, so I'll see you on Wednesday.